So welcome to this little introduction to Bayesian statistics. Of course, we are not going to discuss Bayesian statistics in much detail, but just get an idea of what it is, how it can be used in psychology, and how it is different from the traditional frequentist statistical approach. So if you remember, we discussed today that there have been two different paradigms in the traditional statistics. There was the classical null hypothesis statistical testing approach developed mainly by Ronald Fisher, but also with contributions of others. And he focused mainly on p-levels, mainly on statistical significance. Then Neyman and Pearson developed this paradigm, and they proposed to also focus on effect sizes and statistical power, and to use meta-analytic procedures to combine the findings of different studies. And these are all the things that we have just discussed. However, there is also an alternative approach, completely different, based on completely different ideology, that aims to solve the same problems of knowledge accumulation and of making generalized inferences from samples to general populations. And that's Bayesian approach. Why is it called Bayesian? Because it was created by Reverend Thomas Bayes, or Bayes, who was a priest in the Anglican Church in the 18th century, and he was also interested in mathematics. He was a member of Royal Society, and he proved some interesting theorems, including the Bayes theorem, the main theorem which allows us to calculate conditional probabilities of different events. So here this notation P is for probability, and A vertical line B is a conditional probability. It's a probability of A happening given that B has happened. So it's a conditional probability of A given that B. And you can calculate this probability thanks to Bayes' theorem. Now, I'm not going to explain the Bayes' theorem in much detail because there is a lot of information on that, and also because it's tricky to explain in just a couple of words. But just to give you a very hands-on practical example of how it can be applied. And this example is very modern, 2020 example. Imagine that we are interested in two events. Event A being sick with COVID, or having COVID, being infected with COVID, and event B, getting a positive PCR test result. So imagine that you have gotten a positive PCR test result. What are the chances of you having COVID? It's a very important practical question. Of course, intuition says, oh, if my PCR was positive, it's 100% chance that I have COVID. But as we will see right now, this is not quite true. So our task is, we have these two events, and we are interested in calculating this conditional probability. What is the probability of you having a COVID infection in case if you have obtained a positive PCR test? Now, in order to evaluate this probability, we'll need to know the prior probabilities, the other parts of this equation, B conditional on A, P probability, full probability of A, and full probability of B. Now, probability of A, probability of you having COVID, and it's kind of maybe easy to estimate because we know what is the percentage of people approximately who have COVID at this point in time in this region. Well, let's imagine it's 10% of people who are currently being infected with COVID in this area. The second part of this equation, the probability of getting a positive test result in case if you have COVID. And this is very easy. This is basically test sensitivity. or true positive rate for every test when it's evaluated, when it's validated. Test developers always present this figure. They take a sample of people who are known to have COVID, and they calculate the proportion of true positive results. Basically, the proportion of positive results in this group of people who are known to have COVID. This is called test sensitivity. And you can easily find it in the manual for any test. For PCR tests, it's very different, but it's around 90%. And the hardest probability to come up with is this one, probability of B, probability of getting a positive test. And it's a full probability of getting a positive test. When can you get a positive test? Well, there are two situations. You can get it if you're sick, and you can get it if you're not sick by mistake. So in order to get this, to arrive at this full probability, we need to calculate these two probabilities and add them up. Probability of getting a positive COVID test and having COVID at the same time is a product of probability of having COVID, which we know, P of A, and probability of getting a positive test in case if you have COVID, P of B conditioned on A, and this we also know, it's 0.90. The second part, probability of getting a positive test and not having COVID. This is slightly more tricky. Well, probability of not having COVID is 1 minus probability of having COVID, 1 minus 0.10, because having COVID and not having COVID are two incompatible events. Together, the probability is 1. And this part is probably the hardest one to come up with. It's probability of getting a positive PCR test if you don't have COVID, conditioned on not having COVID. Luckily for us, there is also another statistic which is always published for a PCR test. It's called test specificity, or true negative rate. Test developers take a bunch of people who are known to be healthy, not to have COVID, and they calculate the proportion of negative results in this sample. And this is called true negative rate or test specificity. And in order to calculate this probability, it's basically 1 minus 0.75, 1 minus test specificity. So imagine that for our imaginary COVID test specificity is 0.75. Then this P of B if not A will be 1 minus P of not B if not A. And this will be 0.25, the thing that we are looking for. So now that we know all these four probabilities, we can combine them and calculate a full probability of getting a positive PCR test. And here it's 0.90 multiplied by 0.10, which is part of getting a positive test in case if you're sick. And you can see that actually this probability is not so large altogether of being sick and having a positive test. The probability of being not sick and having a positive test is actually combined larger. It's 0.23 almost. So altogether this full probability of B is 0.315, about 32%. And now that we know all three members of this equation, we can calculate this. Ta-da! And the result is 0.90 multiplied by 0.10 divided by 0.315, about 29%. So if you have a positive PCR test, the chances that you are actually infected with COVID are only 29%. The chances that you are not infected with COVID are about 71%, 1 minus 29%. So there is about 71% chance that you don't have COVID in case if you've gotten a positive PCR test. However, still better stay at home. This is a very realistic, very real life example that shows these the application of these formulas, the formula of full probability and the Bayes theorem. Now, again, if you are interested in more details, there is a nice article on Wikipedia which also shows all these decision trees, like 1 is divided into probability of having COVID and not having COVID, and if you have COVID, it's divided into getting a positive PCR test and not getting, etc. So you can also graphically see how all these probabilities are connected, and what's important is that if you know 3 of them, you can derive all the rest of them using Bayes theorem and using fault probability formula. This is why Bayes theorem is so great, because it allows us to make a lot of inferences by knowing actually very little information. Now, what does it all have to do with psychology? Instead of applying this to the context of a COVID test, we can apply this to the context of any statistical test that we are conducting as researchers. Let's say, for example, event M is the chance of my H1 model being true, and event D is the event of getting this data in my sample. And you can apply Bayes theorem, and you can apply some of these calculations, and you can come up with a statistic which is called Bayes factor, which is very often used. Basically, it's the most important piece of information that you can derive. Bayes factor reflects the ratio of 2 probabilities. The probability of getting this data in case if H1 is true, and the probability of getting this data in case if H0 is true, or the alternative model against which you're comparing is true. Basically, Bayes factor reflects how many times are these data more likely under H1 than under H0, or how strong is the evidence constituted by this data in favor of H0 versus H1. And in order to interpret Bayes factor, we can use this scale which was proposed by Lee and Wagenmakers. They said if this data provides no evidence whatsoever, the ratio of probabilities equals 1. These probabilities of H1 and H0 based on this data are equal. But if we divide the evidence in favor of H1 by the evidence in favor of H0, we can get values of Bayes factor that reflects the ratio of these probabilities. And the stronger is this ratio, the stronger is the support for H1 that we get from this data. And then you can use this Bayes factor to update the prior odds of H1 versus H0 and to generate posterior odds, but we'll come to this in a moment. So if you get a certain value of a Bayes factor, let's say 4, it means that it's a moderate evidence in favor of H1. And if you get, say, a 0.15, it's a moderate evidence in favor of H0. So depending on your Bayes factor, we kind of, it's like a gauge that gauges evidence whether it's in favor of H1 or in favor of H0. To see how it works, let's try to apply it to our previous example of Cinderella. So if you remember from our discussion of effect sizes and null hypothesis tests today, Cinderella performed 5 trials. She drew 5 different samples of grains from this box, and the proportion of white grains was 64, 61, 58, 57, and 65 out of 100. And we can use a special piece of software, JASP, developed by Wagenmakers and colleagues. It's a completely free software which you can download from its website or by googling JASP. which allows you to perform frequentist and Bayesian tests for a number of simple statistical tests, including the binomial test. And I used JASP to evaluate these 5 Cinderella trials. So for each of these trials, the proportion of white grains results in a Bayes factor. For example, the first trial, the Bayes factor is 6.3, and it's a moderate evidence in favor of H1. So H1 is 6.3 times more likely than H0 based on this proportion. In the second trial, it's kind of weaker. It only provides anecdotal evidence, not a strong piece of evidence, and it was only significant at p less than 0.05 as well. And trials 3 and 4, they kind of fail to provide any evidence whatsoever. They are in this range from 0.33 to 1, and it's all anecdotal evidence in favor of H0, but it's not evidence that you can really trust. And the fifth trial, it's a strong evidence in favor of H1. So, the results of Bayesian interpretation correspond to the results of frequentist interpretation. So what's the sense of applying Bayesian statistics? Now, the real power of Bayesian statistics is revealed in the next step. First of all, what we need to understand is that in Bayesian tests, our prior information can be incorporated into analysis. And this prior information is not expressed in the form of a probability, but it's expressed in the form of a probability distribution. So we can very flexibly choose our priors to inform our analysis. Here we call a prior which is called non-informative prior, and it is shown graphically on this picture with a dashed line. Basically, we supply the information that all the possible outcomes are equally likely. All the possible values for the proportion of white grains are equally likely because we don't know what stepmother has put in this box. And after supplying this prior and incorporating the data from this first trial, where we got 64 white grains out of 100, we get this posterior distribution, the distribution which combines prior information and the data. And the median of this posterior distribution is kind of 0.64. And there is also a credibility interval. A credibility interval which is very similar to confidence interval. It reflects the boundaries in which the true value of the effect is supposed to lie with 95% probability. And substantially, it's very different from confidence interval. But in practice, it's pretty much the same. And numerically, it corresponds to our estimate of confidence interval based on frequentist statistics. Now, how can we incorporate the next trials? Now we can use this posterior distribution from this first trial as a prior for the second trial. And this is what happens. So we can model this distribution that we got from the first trial as a prior for the second trial. And in the second trial, we got something like 61 white grains out of 100. And as a result, this updates our information. The median shifts a little bit to the left. It's now 0.625. The confidence interval, credibility interval, is now slightly more narrow. But based on those two trials combined, the Bayes factor is 7.29, so almost 7.3. And this constitutes a stronger evidence in favor of H1 than trial 1 or trial 2 taken independently. So we have combined them and we have arrived at a stronger evidence. Now what happens if we combine two weaker trials, two trials where we didn't get a significant result? I have taken here the results of trial 3 taken independently, and I added trial 4. And based on those two trials alone, as if the other three did not exist, we get a median estimate of effect of 0.57, and the credibility interval is again equal to our confidence interval that we got based on frequentist statistics. I just rounded it to the second digit there, and here Jasper did not round it. However, in frequentist approach, we gave an interpretation that it's a significant effect because P was almost 0.01, at least it was below 0.05. However, in Bayesian approach, based on these two trials, 3 and 4, the combined Bayes factor is only 1.87, which suggests anecdotal evidence in favor of H1, but not strong enough to confidently accept H1. So Bayesian approach might give us more credible information because we make those interpretations more carefully. So this was just a very quick, very simple example. Of course, there are very many differences between frequentist statistics and Bayesian statistics. The most important difference is that in frequentist statistics, we take our data and we say, okay, our data are biased, imprecise, but we'll use this data to make an assumption in favor of H1 or of keeping H0 as an assumption about what happens in the general population. However, in the frequentist approach, we can never be sure whether H1 or H0 is really true, and we can never evaluate directly the probability of H1 or H0. In Bayesian statistics, this is exactly what we do. We try to evaluate directly the probability of the null hypothesis or H1. And another advantage of Bayesian approach, in frequentist statistics, we normally rely on normal theory. However, in very small samples, our estimates based on normal theory are very unstable, and our conclusions based on normal theory are not so strong. Bayesian statistics don't make any distributional assumptions whatsoever. That's why in small samples, Bayesian statistics work much better. And also, Bayesian statistics make it easier to incorporate prior knowledge. Of course, in frequentist statistics, you can do meta-analysis, you can combine the results of independent studies, but you cannot really incorporate a hypothesis about a certain prior distribution. That is too complicated. And so on. There are also other important differences. And you can read the paper by Rens van der Schot and colleagues, A Gentle Introduction to Bayesian Analysis, where they describe all these differences in detail. However, Bayesian approach also has some disadvantages. First, it's more complex. It's more difficult to apply and to interpret. That's why if you are applying Bayesian approach in your paper, you need to be prepared that it will be very hard to find reviewers to review this paper, at least at present, because many people are not familiar with the application of Bayesian approach. Another disadvantage is that because it's more complicated, it offers more degrees of flexibility. For example, by choosing different prior distributions, you can influence to some extent the estimates that you get as a result. Now, this gives a researcher more flexibility, but it also gives a researcher more degrees of freedom. And I think I saw somewhere some research showing that if a researcher was trying to manipulate their conclusions, it was easier to do it using Bayesian approach than using frequentist approach, because you can choose different priors. And so far, the standards concerning which priors to use for which situations are not yet completely clear. That's why if you are doing something simple like the t-test or a correlation or a binomial test, probably it makes no sense to use Bayesian statistics, at least at present. I'm not a super big fan of Bayesian statistics, as you can see. But some people are very optimistic about it, and maybe in a couple of years the situation will change completely. However, already at present, there are areas in applied psychology, there are applications where Bayesian statistics are much superior to frequentist statistics. One example is psychometrics. Basically, any models that involve a large number of parameters work better with Bayesian statistics. For example, complex confirmatory factor analysis or complex structural equation models, where there are many loadings, there are many cross-loadings. In Bayesian statistics, you can set priors for these cross-loadings to be not exactly zero, but to vary in a certain range. And as a result, this model is easier to converge. It provides more reliable estimates, and it's more flexible. It allows for more flexibility. It allows to model the data in more realistic ways compared to classical frequentist models, where, for example, you assume that cross-loadings are exactly zero, that the differences between groups are also either exactly zero or non-zero, etc. So for investigating psychometric structures of very large questionnaires, or for testing measurement invariance with very large numbers of groups, Bayesian statistics are superior. And of course, the situations of machine learning, when we develop some kind of mathematical models that are continuously updated by the data that is being fed in, Bayesian approach is also very promising and is often used for applications like natural language processing. So if you're interested in those areas, probably it makes sense to spend some time with Bayesian models. If you just wanted to understand general idea of Bayesian approach, this is the general conclusion. That traditional frequentist approach treats our data as biased evidence to make choices between simple assumptions, simple models of reality H1 or H0, but you can never know which one is exactly true. However, you can evaluate the probability of your assumptions. In Bayesian approach, it's like a frequentist approach upside down. You use your data to inform your model. You integrate your data into your model to improve your vision of reality, to make it more precise, to make your prediction better. So people who use Bayesian statistics a lot, they argue that Bayesian approach is more intuitive to a human mind. I don't know. I think it depends on what you're really used to. So if you're interested in reading more on Bayesian statistics, there are two papers that I like by Rens van de Schot that provide a nice introduction. I did not put them into our folder to avoid creating confusion, but you can easily find them online. And there are also two papers by Eric Wagenmakers, the creator of JASP, with his colleagues, where they describe the basics of Bayesian inference, and they also provide examples of simple Bayesian alternatives of classical statistical tests like t-tests, correlations, etc., to argue that Bayesian approach is better. But, well, if you're interested, it's up to you to try it and decide. And JASP is probably the software of choice. It's much more convenient than R for Bayesian statistics. So thank you for your bravery and your motivation to get through this approach. I cannot say I'm very confident in it myself either, but I think at least understanding the basics is important to maybe use Bayesian psychometrics, because that's one very useful area. So good luck in exploring Bayesian statistics, and see you soon in our next lecture. Bye bye.